Good morning. I wanted to take a little bit of time today to go through the Nernst equation again. And so I wanted to make sure that everybody understands how the change in composition affects the Gibbs energy and therefore how it affects the cell potential. So just as a quick reminder, our Gibbs energy is based on this understanding that depending on where the composition is, so over here on the left I've got all reactants and over here I've got all products, and then the reaction will naturally go forward to wherever the equilibrium composition is, and I drew it here at about 1/3 of the way forward. So this is not a hugely product favored reaction, but it is one that will go forward at some point. So we know that once we get to the equilibrium composition, we can describe the energy that was associated with getting there as this delta G naught equals minus RT natural log of K. And from chapter 14, we also have the expression that if we are at some non-equilibrium situation, so we've got the reaction quotient instead. And remember that the reaction quotient describes some composition that is either before equilibrium or after equilibrium. And so that means that if, of course, we've got Q less than K, then the reaction will go forward in the spontaneous direction here. And if we've got Q greater than K, then the spontaneous direction will be in the reverse. And that's what this equation right here describes. It is describing the Gibbs energy between where we are and where equilibrium is. So this is the delta G if we were at this composition and we were going forward. That's how much that would change. So so this applies then, and we know that we can convert between the Gibbs energy and the cell potential. And so similarly, we can take this equation and turn this into our cell potential for a situation when we don't have standard state conditions or equilibrium conditions, and that is this equation. So this Q is still the reaction quotient, the R is the gas constant, and F is the Faraday constant, and then N is the number of moles of electrons that are involved in the electrochemical cell that we're talking about, and then everything else kind of temperature, of course. And then this is the standard state cell potential there. All right, so let's consider an actual cell. I just picked a couple of reduction potentials. So the reduction potentials that I picked, I just went with chlorine, and tin. Okay, so good practice right here for just one moment is to look at these two reduction potentials and decide which one of them is going to be the cathode and which one of them is the anode. So you can pause the video if you need some time to think about it. Otherwise, just take a moment there and think about that real quick. So here's our reminder, which is that if things are higher in their cell potential on the reduction potentials, that means that they are probably going to be the cathode because there is more energy released when they are reduced. Okay, so cathode is reduction, and the tin is then going to be the anode. Okay, so we're going to go ahead and see how much difference it makes if we change the concentrations from standard state. So remember, standard state means that for anything that is aqueous, then the concentration is going to be 1 molar, and for gases, it's going to be 1 bar. And we can use these interchangeably in our equilibrium constant expression. So, in order for us to do this, we're going to need to know, like what the actual reactants and products are, so we can write an equilibrium constant expression, or rather a reaction quotient expression. So that means we need to translate these sets of equations into a real equation. So the easier way to do that might actually be to start with your cell potential. So again, good practice. Remember our standard cell notation. We have the oxidation reaction happening on the left and the reduction happening on the right, and then this is our salt bridge indication. And so the oxidation means that we're going to go in the direction of loss of electrons. So our anode is the one that is doing the oxidation, so that's tin. So we're going to go from tin 2 plus to tin 4 plus. And then chlorine is going to go in the direction of the reduction, which it already is. So chlorine gas and 2 chloride. Okay, so perhaps this helps, and if not, it's still good practice here. So the other thing to remember is that this vertical bar, which is a physical separation between our states, and in this case, it's going to be a little harder to tell why. It's physical, but anyway, the other thing that you can do with this vertical bar is to recognize that this is like the arrow between the reactants and the products for both of these. So that means that when we translate this to a balanced chemical equation, we have tin as a reactant and chlorine gas as a reactant. Those are the two on the left-hand side of that arrow. And then overall, we're going to make tin 4 plus and 2 chlorides. Okay? So this is now enough information that we can write our reaction quotient expression. So products over reactants, we'll have tin. I'm just going to go ahead and write everything as concentrations. So there's 2, so that's squared. Tin 2 plus and chlorine gas. Okay. So standard state would be 1 molar concentration of everything here. So let's try some numbers that would be at a different concentration than standard state. So I just picked some. Let's say that both of our concentrations here for our products, or excuse me, for our reactants are at 2 molar, and that all of our products happen to be at 0.5 molar. And you can pick any numbers you want. And the next worksheet will have some practice problems where you're doing this too. Okay, so when we calculate our E cell, we need to include all of this information. So RT natural log of Q over NF. So we did need that cell potential. So going back up to our cell, this is our cathode and our anode cell potentials. So our E cell for the standard state is cathode minus anode, 1.358 volts minus 0.154 volts. So that is 1.204 volts. All right. And then we need a little bit more information, which is we need the temperature. So we'll just go ahead and go with room temperature, 298 Kelvin. And then notice that this reaction does involve 2 electrons. So that's the number that is going to go in here. So take a moment and set up your equation here. And then, so if you want, pause the video, put in your cell potential, put in your R, your T, natural log of Q, and over NF. So put in all these values and calculate the cell, and then unpause the video and come back and we'll look at the results together. So hopefully you went ahead and did that. I'm going to go ahead and put my numbers in. R will be 8.3145 joules per mole Kelvin, 298.15 Kelvin. And I'm going to do all of the RT over NF first, and then I'm going to do the natural log of Q. So that's 2 moles of electrons, and the Faraday constant, 9.648 times 10 to the 4 coulombs per mole of electrons. And then Q, we will have 0.5 and 0.5 squared, and then 2 and 2. Okay, so in my intermediate work here, this first number I get 0.01285, and let's see, the units will be kelvins cancel, these moles of electrons cancel, so we will have joules per mole C. I feel like I need a mole to cancel out another mole. Anyway, I'm not going to worry about it. Natural log of 3125. So I'll probably have to go away because I can never think about things super fast. I'll have to go away and figure out where the other mole goes away to. But I'm confident that the units do work out here. So this number times this number turns into 1.204 volts minus a negative 0.04453. And then just a reminder that joules over coulomb is equal to volts. And so these will both end up being volts, so that our non-standard cell potential will be 1.249 volts. So this isn't a lot different. As we saw in class, these numbers do not change a whole lot when we change the composition, but it will change a little bit. So if you want to practice this again, you can just go back and do the same thing that I did, which is pick a cathode and an anode, and then pick some compositions here, and then just go through and practice those calculations. So let me know if you have any questions about this, and otherwise I will continue on to the next topic.